You ever wonder how a computer can take just a total jumble of information and instantly get it with perfect clarity? Well, the secret, it's one of the most elegant ideas in all of computer science, the tree. It's this amazing invisible structure that turns chaos into perfect logical order.
Okay, let's start with a super quick math quiz. Take a look at this. 1 plus 2 times 3. Simple, right? You probably figured out the answer in a heartbeat. But how would a computer solve it? And as you're about to see, that question is a lot trickier than it looks. See, if you just go left to right, add first, you get 9. But if you remember your grade school math, the order of operations, you multiply first and you get 7. For us, it's a little confusing, maybe. But for a computer needs absolute certainty. This kind of ambiguity, it's a total deal breaker.
And this little math problem, it really just hits the nail on the head. It shows the challenge perfectly. Computers can't just know the order of operations the way we do. They need a system, a structure that leaves absolutely zero room for doubt.
Yeah, they need a way to build the correct order of operations right into the data itself. And that, my friends, is where the hero of our story comes in. So, the solution? It's this brilliantly simple data structure called a tree. What it does is it organizes information in a hierarchy. It turns that flat, confusing line of text into a structure where every single relationship is just crystal clear.
Okay, so what is a tree, really? Well, formally, it's built from these individual things called nodes. Just think of each node as a little container. It holds one piece of data, and it holds pointers that connect it to other nodes. That's it. That's the basic building block.
So, how do we actually build one? Well, every tree has got to start somewhere, right? And that single, most important node at the very, very top, the one where everything else grows from, that's called the root.
And from that root, we start to branch out. Any node can point to other nodes below it, and we call these its children. And boom, that's what creates the hierarchy.
And finally, what happens when a branch reaches its end? Well, you get a node with no children of its own. And just like a real tree, we call these leaf nodes. They're basically the endpoints of our whole data structure.
Now look, trees can get pretty complex for sure. But for this explainer, we're going to focus on a really common and super useful type, the binary tree. The rule here is dead simple. Each node can have at most 2 children, a left one and a right one. That's it.
All right, let's bring this all back home and finally solve our original math problem. We can actually represent that expression, 1 plus 2 times 3, using a special kind of binary tree. It's called an expression tree.
And what's so clever about this is the rule for building the tree. It's so simple. The numbers, what we call operands, they're always the leaves, the endpoints. And the math symbols, the plus, the time sign, the operators, they're always the parent nodes that connect everything.
Okay, so let's actually build it. All we have to do is follow the exact same order of operations we all learned back in school. Multiplication happens before addition. That one single rule, that is the key to building this tree perfectly.
So we're going to start from the bottom up with the highest priority operation. For us, that's the multiplication, right? So the multiplication symbol becomes a parent node, and its 2 children are the numbers it's working on, 2 and 3.
Okay, next up, the addition operator. It connects the number 1 to the result of that whole multiplication branch we just made. And just like that, the plus sign becomes the new root of the entire tree. See what happened there? The structure itself now forces the correct order. The ambiguity? It's totally gone.
But this is where it gets really cool. Once you have this one single perfect tree, the way you decide to walk through it, or traverse it as we say, can actually produce totally different but equally valid ways of writing the same expression.
So let's try our first walk. This one's called an in-order traversal, and the rule is super simple. You always visit the left child first, then the node itself, and then the right child. Left node right. Got it?
Okay, so if we apply that rule, left node right, to our tree, what do we get? Well, we get 1 plus the result of 2 times 3. Hey, it perfectly recreates our original expression. This is called infix notation, and it's called that because the operator is in between the numbers. It's exactly how we humans naturally read math.
Okay, but what if we just tweak the walking instructions a little bit? Let's try a pre-order traversal. This time, we visit the parent node first, then the left child,
then the right. So node, left, right. So if we follow that new rule, node, left, right, we get plus 1 times 2, 3. Yeah, it looks totally bizarre to us, I know, but this prefix notation, it's absolutely fantastic for computers. Why? Because the operator always comes before the numbers it applies to. That means the computer never has to guess about the order of operations. It is completely 100% unambiguous.
And for our last walk, I bet you can guess the pattern by now. This is post-order traversal. We visit the left child, then the right child, and then finally the parent node itself. Left, right, node.
And this walk gives us 1, 2, 3 times plus. This is called postfix notation. You might have also heard it called reverse Polish notation. And just like prefix, it's perfectly clear for our machine. In fact, this was the logic behind a lot of early calculators.
So here's the big takeaway. Check this out. From one single, perfectly structured tree, we just generated 3 completely different ways of writing the same thing, just by changing the order we visit the nodes. I mean, how cool is that? It just shows how a simple little hierarchy can create so much power and utility.
Now you might be thinking, okay, that's a neat trick for solving a math problem, but so what? Well, this concept is absolutely everywhere. It's underpinning so much of the digital world that you and I interact with every single day.
I mean, think about it. Searching for a file on your computer. The reason that's so fast is because the data is sorted in a tree. Or what about your computer's file system? You know, with folders inside of other folders. Yep, that's just a giant tree structure. And when a programmer writes code, the compiler builds an expression tree, just like the one we made, to understand all the logic and turn it into a program that actually works.
Ultimately, it all comes back to this one really powerful idea. Trees give us a natural, an elegant, and pretty much a foolproof way to represent structure and just get rid of ambiguity. They take what could be total chaos and turn it into perfect, machine-readable order.
So the next time you type something into a search bar, or open a folder, or run a program, and it just works, maybe take a second and ask yourself, what invisible tree is working behind the scenes right now, silently making sense of it all?